Understanding LLM architecture and its significance is closely tied to transfer learning and adaptation, which are vital techniques in machine learning. These approaches allow us to leverage knowledge gained from one task or domain and effectively apply it to the new tasks, resulting in the development of powerful language models. Transfer learning involves utilizing a pre-trained model trained on a large dataset as a starting point for a few tasks. Instead of training the model from scratch on the new task, transfer learning initiates it with the pre-trained weights and fine-tunes it on a smaller labeled dataset specific to the new task. This way, the model adapts its pre-learned representations to the specific patterns and characteristics of the new data. Transfer learning proves particularly advantageous when the new task lacks labeled data or requires substantial time and resources to train from scratch. On the other hand, adaptation, also known as domain adaptation, focuses on addressing domain differences between the source and target domains. It aims to adapt a model trained on a source domain to perform well on a target domain where labeled data might be scarce or unavailable. The key challenge in adaptation is to ensure that the model generalizes effectively to the target domain despite distribution shifts. Adaptation techniques work towards aligning the representations learned from the source domain with those of the target domain, reducing the domain discrepancy. By gaining insights into transfer learning and adaptation in the context of LLM architecture, researchers and practitioners can fully exploit the potential of large language models. The ability to effectively apply existing knowledge and adapt to new challenges empowers these models to achieve groundbreaking results in language-related tasks, making them indispensable tools in the field of natural language processing. Let's learn now about the various approaches to adaptation. Imagine you have a smart robot that can recognize objects like cats, dogs, and cars. It learned how to do this by looking at many pictures with labels, so it knows what each object looks like. Now, you want this robot to work in a new place where it hasn't seen any pictures before, but there are similar objects like cats, dogs, and cars. To help the robot adapt to this new place, you can use different approaches. Feature-based adaptation. This is like giving the robot special glasses that help it to see the world in a way that's easier to understand. The robot tries to find common features or characteristics between the objects it already knows from the old place and the objects in the new place. By doing this, it can create a new set of features that work well for both places, making it easier for the robot to recognize objects in the new environment. Instance-based adaptation. Instead of changing the way the robot looks at things, instance-based adaptation focuses on adjusting how much attention it pays to each object in the new place. The robot looks at a mix of old and new pictures, and it gives more importance to the pictures that look similar to the new place. This way, it can learn to recognize objects in the new environment based on the examples it finds most relevant. Model-based adaptation. Imagine the robot has different parts in its brain responsible for recognizing different types of objects. Model-based adaptation involves fine-tuning or adjusting these parts to be more specific to the new place. It's like teaching the robot to pay more attention to the details that matter in the new environment, so it becomes better at recognizing objects there. Transfer learning and adaptation can thus be likened to teaching a robot to apply its previous knowledge wisely when it encounters new situations. This enables the robot to recognize objects in novel environments, even if it hasn't encountered those exact objects before. The advantage of these techniques lie in their ability to save time and resources, as the robot doesn't need to learn everything from scratch each time. Instead, it builds upon its existing knowledge and adapts it to tackle new challenges effectively. These powerful techniques extend beyond robotics and find application in various fields. In the computer vision field, they aid in recognizing objects under different conditions, while in natural language processing, they assist in understanding and generating text in diverse contexts. By harnessing prior knowledge and adapting it to novel situations, these approaches enhance the versatility, efficiency, and accuracy of machine learning models when faced with new and unfamiliar tasks or domains. In the context of large language models, fine-tuning takes adaptation to an advanced level, empowering the models to acquire specific styles, personalities, and domain-specific knowledge. The process begins with a pre-trained LLM, which has garnered general language understanding from a vast text corpus. However, this pre-training is generic and not tailored to any specific application. That's where our specialized tool, LLM Studio, comes into place. LLM Studio allows researchers and practitioners to fine-tune the LLM on task-specific or in-domain data, making it more applicable to particular tasks or domains. In the following modules, you will have the occasion to learn more about this wonderful tool, but we need to cover a couple of more concepts before that. As for the moment, please keep in mind that during the fine-tuning phase, the LLM adapts its knowledge to better align with the target task, enabling it to generate responses that match specific writing styles or adapt distinct personalities. For example, it can be fine-tuned on customer support conversations to respond empathetically and politely, or on creative writing samples to generate text in a poetic or storytelling manner. The process of fine-tuning equips LLMs with exceptional versatility, allowing them to cater to various specific needs and providing invaluable information across a wide range of language-related applications. For a more in-depth understanding of how to use LLM Studio and leverage fine-tuning for specific tasks, we invite you to stay tuned and continue our LLM learning path. Understanding the large language model architecture is crucial for effective utilization in natural language processing tasks. Familiarity with LLM architecture empowers researchers and practitioners to leverage their capabilities, such as capturing contextual information, handling long-range dependencies, and generating high-quality outputs. This understanding facilitates the design of better applications, improves model performance, and enhances various language-related tasks. Throughout this class, we covered a range of topics related to neural networks, deep learning, the transformer architecture, pre-training and fine-tuning of LLMs, as well as transfer learning and adaptation. We began with an introduction to neural networks and deep learning, which have revolutionized various fields, including computer vision and natural language processing. Next, we focused on the powerful transformer architecture, which employs self-attention mechanisms to efficiently capture relationships between words and handle long-range dependencies. The transformer has been widely adapted in tasks such as machine translation, text generation, and sentiment analysis. We explored the concept of pre-training and fine-tuning of LLMs, which involves training models on large amounts of unlabeled text data to capture general language understanding, and then adapting them to specific tasks using task-specific labeled data. This approach has proven effective in leveraging existing knowledge and accelerating learning on new tasks. During our exploration, we encountered various types of pre-trained models such as H2O-GPT, BERT, and Roberta, which have greatly influenced NLP tasks and achieved top-notch performance. Lastly, we discussed transfer learning and adaptation, which enable models to leverage knowledge from one task or domain and apply it to another, saving training time and resources, especially when labeled data is limited. Adaptation techniques address domain differences, allowing models to generalize well to new domains despite distribution shifts. To put it concisely, this class has established the foundational principles of modern language models, covering crucial concepts in neural networks, the transformer architecture, pre-training, fine-tuning of language models, transfer learning, and adaptation. These breakthroughs have triggered a revolution in natural language processing, driving substantial advancements in language comprehension, generation, and practical implementation across diverse domains, all empowered by the revolutionary capabilities of foundation models. Looking ahead, our next focus will be on another critical component in LLM's construction, the data prep step, and its significance in preparing data before fine-tuning. Fortunately, H2O AI offers a fantastic tool, the LLM Data Studio, to assist you in this process. Feel encouraged to delve into the subsequent modules within this series for a more comprehensive exploration. This will enable you to fortify our comprehension of data preparation techniques with the aid of our LLM Data Studio, attain mastery over the intricacies of fine-tuning via our LLM Studio, create and refine your individualized LLMs by incorporating your unique dataset, employ evaluation techniques with the guidance of our LLM Eval tool, immerse yourself deeply in practical applications and case studies utilizing App Studio and Helium. These segments are meticulously crafted to amplify your expertise and hands-on capabilities within the realm of LLMs, ensuring your readiness to tackle the intricacies of real-world scenarios. In the upcoming module, we will guide you through the data preparation process, exploring simplified and code-free methods to establish an effective data flow. We are eagerly anticipating your participation in the upcoming course. Cheers!